Hi, my name is Cindy Schmidt, and I'm with the University Corporation for Atmospheric Research in Boulder, Colorado. I'm very pleased to introduce Gerald Meehl, Senior Scientist at the National Center for Atmospheric Research. Dr. Meehl is an internationally recognized and highly cited expert on climate variability and climate change, with over 200 peer-reviewed articles to his name. Dr. Meehl has served on many national and international scientific committees, of which I will mention only one, but it's a big one. That is his work on all assessment reports of the Intergovernmental Panel on Climate Change, or the IPCC. He was a contributing author in 1990, a lead author in 1995, and a coordinating lead author in both 2001 and 2007. In 2013, he served as a fifth assessment report lead author for Working Group 1, the Physical Science Basis. His talk today focuses on the IPCC process, as well as the scientific findings of Working Group 1, including some distinctions between the fourth and fifth assessment results. Jerry?
Thanks, Cindy. So as Cindy said, I'm going to be talking a little bit about the background of the process that went into producing the AR5 and then some results that came out of it, both some of the observational results and the projections and predictions. So just to kind of give an overview, wanted to say a little bit about IPCC in general, and then the structure and how the IPCC Fifth Assessment Report from Work Group 1 kind of went. Say a little bit about what's new compared to the AR4, because that's kind of a question some people ask, and then some results from it. So what is the IPCC? Well, contrary to popular belief, the IPCC is not a group of scientists, it's a group of governments. It's the Intergovernmental Panel on Climate Change. So it's about 190 governments, kind of organized under the UN framework. And the governments got together in the late 1980s and said, you know, we really are hearing about human-caused climate change, but we don't really know much about it, and we want information that may impact policy decisions. So they kind of organized themselves, and they commissioned the scientific community to produce these reports. And so they kind of divided it up into three working groups based on kind of general topics of information they wanted to hear about. One was physical climate science, which is Working Group 1, which is what I'm going to be talking about today. Working Group 2 is climate impacts and adaptation, and Working Group 3 is mitigation. So the way this was set up was it was between UNEP and the WMO, both part of the UN, and like I said, in the late 80s, they got together, and the UN General Assembly finally endorsed their proposal and established the IPCC. So what are these assessments? Well, the idea is, and what the scientists are told when we start doing these reports, the instructions from the governments are, they want to know the current state of human knowledge on climate variability and climate change. It's a fairly sweeping kind of mission, but that's kind of what they want to know. The other distinction about these assessments, they're assessments, not reviews. So if you're writing a review paper, and scientists are very familiar with writing review papers, you basically go through the literature, say, okay, this paper said this paper said that, this paper said that. In the end, you summarize all of these kind of results. But in assessment, you do all that, and at the end, you say what you actually think is happening. So you have to come down on the side of what you actually, at that point in time, what the best in your expert judgment is actually occurring. And of course, this may change with succeeding assessments, but that really is what distinguishes an assessment from a review. And in the process, we're constantly reminded that this is an assessment, not a review. You have to actually, in the end, say what you think is really happening. And another kind of instruction that's kind of a mantra that you hear a lot is, this is policy relevant, not policy prescriptive. So this is a very firm line that's drawn. The scientists are providing information that the governments want to know about that can inform their decisions, but the scientists can't tell the governments what to do with this information. So that's a real kind of a key point that we're reminded of a lot when we participate in these things. And because these things are so high profile, they have to be really transparent. So they've set up over time 2 stages of open international review. So anybody really could have gone on the web page and signed up to review any part of the AR5. And of course, we get thousands of comments. And each chapter for each round of review And these are 14 chapters. We got on the order of 1,500 comments at each step of the review. And because this is very transparent, we get these in a big Excel spreadsheet, and we have to go through and respond and fill out this Excel spreadsheet, responding to each one of these comments, saying what we thought about it, whether we agreed or disagreed, and what we did to edit the document if we did anything. And this is to keep from a reviewer coming back and saying, hey, well, I submitted a comment and you ignored it. You say, no, we didn't ignore it. And you can go right to the Excel spreadsheet and say, here's what we did with your comment, and this is how we responded to it. So this is a really important part of this. It has to be traceable. Everything has to be traceable. And then there's this kind of weird calibrated uncertainty language. And this kind of was instituted because as part of the assessment. So when you're coming down to these conclusions, you're making expert judgments, how do you kind of quantify what your expert judgments are? And that's in this kind of a chart. The certainty scale, which is the one in the upper right here, goes from virtually certain, in other words, you're 99% certain that your conclusion is probably true. Extremely likely is 95% certain. Very likely, you think it's about 90%, you're sure of that. Likely is 66% and on down. So usually when you read the chapters, the categories that get used the most are likely, very likely, and extremely likely. So those are pretty easy to understand, and you're for scientists, you're thinking in probability terms. You're thinking, well, most of the literature is looking this way. We think this is what is happening. We think it's likely that this is occurring or may occur in the future, or whatever you decide on. And then there's this kind of agreement scale that you kind of can factor in, and that's the lower right part of this. The amount of evidence you have and the amount of agreement you get in the evidence. And this is more difficult for the scientists to understand how to apply this. And we were encouraged a lot of times to kind of combine a likelihood assessment with an agreement or an evidence statement. And so you're trying to do this as part of the assessment to give an idea in a kind of uniform way across all the chapters as to what you think is really going on and how certain you are of it. So as Cindy mentioned, there's been 5 of these assessment reports. The first was in 1990, the second was in 95, third was in 2001, fourth 2007, and the one we just completed was in 2013. So the question is there going to be a 6th assessment report? And we don't know that. It's up to the governments to decide whether or not there's going to be a 6th assessment report, and I'll say a little bit more about that at the end. So over the years, there's been some controversies, and these controversies have really kind of marked the progression of how visible this climate change issue is, not only in the public eye, but in the kind of policy realm. And the first time we really got an indication that there were powerful forces out there that may not like what we were saying in terms of the science was in 1995. And at the Madrid plenary in 1995, and it was still kind of early days. It was only the 2nd assessment report. So we're kind of going through the usual thing, and the governments are making comments, and we're changing some of the words in the summary for policymakers to make sure they were communicated correctly. And this was all done as agreed to beforehand. None of this procedure had been written down, however. So what happened was, at the end of the plenary, the lead authors had to go back in, and we had these track changes versions of MS Word documents and make sure all of the changes got in. And somebody got a hold of a version of the summary for policymakers, which is this kind of shortened version of all the conclusions of the report, the version that was going into the plenary and the version that came out, and they did a match, and they said, oh, well, the lead authors made all these changes. And the implication was that the authors were spinning the report after the plenary, after the governments had seen it, to make unauthorized changes. So by raising this issue, it became an ethical question that these scientists were ethically challenged. They were out to convey a certain message, and they made these changes, and it became a huge report. Certain lead authors were attacked personally in the front pages of publications like the Wall Street Journal and other places, and it became a very stressful situation. We realized at first we thought, well, they just don't understand. If we just explain it to them, logically and rationally, as scientists would do, this is how we approach things, they just understand. If we just explain it to them, then everything will be okay. It was only later we realized that these people that were attacking us understood perfectly what the process was. They probably had a better understanding of the science than a lot of climate scientists did. They were using that to find gaps and weak spots to attack it. And so that was a real eye-opening experience. And so after that, they instituted review editors that would kind of stand between the people that are attacking the process and the lead authors who actually wrote the report. And so ever since then, and the review editors act kind of like editors at journals. So it was kind of a procedure that we were familiar with, and that's worked well ever since then. But we had to kind of learn that the hard way. Then another kind of incident that occurred was after 2007, the AR4 was completed. In 2009, we had this stolen email incident that some people refer to as Climategate. And of course, there was a lot of interesting reading among the emails. Scientists, being kind of snippy with each other, would be sending emails back and forth. And of course, these things taken out of context look pretty bad in certain cases. But of course, what they were trying to do was to attack scientists' credibility. And therefore, if you can say that the credibility of the scientists is bad, that they're doing things that are kind of behind the scenes and trying to conspire to come up with various results, then that would discredit the IPCC assessment reports. So it was a huge media kerfuffle. There were then multiple subsequent investigations in the US and the UK have cleared those scientists of any wrongdoing. It all finally kind of calmed down, even though people still bring this up, but it was kind of beaten back in a number of different places, and the Air Force science still stands. Then there was this thing that came up that there were errors in the AR4. 2 minor errors were found. Both were in the Working Group 2 report. They were on the Himalayan glaciers and the area of the Netherlands below sea level. Both of them, one was actually kind of a typo, amazingly enough, that a typo could slip through after many hundreds of people have read documents, but inevitably there's always errors that come through. But Working Group 2 didn't have a good errata procedure. So usually if a journal article is published with an error, there's a standard procedure where the editor gets involved and the authors are contacted, they submit a correction, it's published, there's a standard procedure. IPCC didn't have a standard procedure to do that. Now we do. So that is something that's been dealt with, and again, we had to learn that the hard way. So this is a kind of a complicated slide. Just to let you know, it's a very long and a kind of arduous process to produce one of these assessments. The fifth assessment report started in 2009 with these scoping meetings where the governments get together with the scientists. The governments raise issues that they would like to see addressed. They say, okay, we want this kind of information, and they kind of commission the scientists to then go ahead and follow a certain outline of topics they want addressed. Lead authors are nominated in 2010. This is another very formal process. In the US, anybody could have nominated anybody to be a lead author. The names all went into a committee, agency people in DC. They boiled it down to a short list. That went to the international level, to the IPCC, which then took all of the nominations from all the countries into account and tried to then for each chapter get expertise balance, gender balance, developing country versus developed country balance, every kind of balance you can think of to get these teams to be kind of covering as many bases as possible. There were 4 lead author meetings where we worked on various versions of the draft, and they're highlighted in red there. And these lead author meetings are hosted by countries who compete to actually host these lead author meetings. So it's viewed by your country as something that's fairly important that you host, that you can say you hosted an IPCC lead author meeting, and they try to spread them around to geographical areas. The first was in China, representing Asia. The second one is in France, representing Europe. The third was in Morocco, representing Africa. And the fourth was in Australia. So you have to go to all these meetings. We work on various versions of drafts. There was 2 rounds of review. Some of the time we spend at lead author meetings is going over all these comments we get, these thousands of comments. And a lot of times at the lead author meetings, we coordinate among the different chapters of who's covering what. So we want to avoid overlap. So we have these cross-chapter breakout meetings. You say, okay, well, is your chapter doing this? No, we're doing that. No, well, you should take that. We'll take this. And you try to make sure that everybody's got all the bases covered and there's no gaps. So just a little bit about, again, the structure, starting at the bottom left here. Again, like I said, in 2009, it kind of started. There were 255 authors from 39 countries. 18% were female, 24% were from developing country or economies in transition, and about 50% were new to the IPCC. And this is another thing that's important. You don't want to have all the same people like me doing all the reports. You want to kind of rotate them through. And you thought that I would have rotated through by now, but hopefully I have by now. And then we go through this 2 rounds of review. We got almost 55,000 comments from over 1,000 people. There were 14 chapters, and then this all comes down to the summary for policymakers, which summarizes all this in 27 pages, and that's when the government show up to approve all these conclusions word for word. Just a little bit about the structure. This is kind of the outline, but the general categories, there's observations, processes, forcings, future climate change, some integration. There was a sealable change chapter this time, which wasn't in the AR4, which was in the AR3 actually, and they decided to bring it back because it was a fairly major set of literature that had to be assessed. And chapter 14 was this climate phenomena and regional climate change chapter. So at the bottom there, I say it kind of gets boiled down into 2 products. So you get all these chapters that are written kind of at the level that scientists would write technical documents. And grad students read them, and they're a great resource for grad students, I've always said. But if you want to get something that's a little bit more shortened, you can go to the technical summary, which is about 150 pages. And that's taking the major conclusions from all the chapters and putting them in place. And then you boil that down into this 27-page document called the Summary for Policymakers, or SPM. And that is extremely carefully worded in very concise, compact statements that the governments can read and hopefully understand. And that's the document that is gone over in this IPCC final plenary. This is where all the governments come together and you basically deliver your product. And the product delivery part is going over the Summary for Policymakers line by line. And this takes 4 days. And you go late in the night and early in the morning in many cases. People say, what do you spend all that time doing? Well, I would guess 85% of the time is basically a wordsmithing exercise. So governments will say, well, I don't understand that word, or that phrase doesn't make sense to me, or what do you mean by that? And so you're trying to clarify. And the scientists, there's, of this 255 some authors, there's about 50 of us who are at Stockholm there to make sure that the science doesn't get changed. So the scientists have to agree to wording changes, and you try to decide, okay, is that wording okay? Okay, then we'll make that change, and you go through the whole document that way. But about 15% is certain governments are trying to spin the document in certain ways. Some governments try to weaken it to make it less certain. Other governments are trying to strengthen it because they think it's a stronger case. So those are the that time is really when the scientists have to be on alert, because you want to make sure that governments aren't changing the science. And that's why the scientists are there to make sure that happens. So some people think this plenary, the governments get in there and just make all the changes and it becomes a political document. That's not right. It becomes a document that governments can read and understand, hopefully. And that's the point of the exercise. So this was the scene in Stockholm in September. This was the big plenary. There were about 110 of the 190 governments had delegations, or about 300 delegates. There was simultaneous translation into the 6 UN languages. And if you look in the upper left-hand corner of that picture, you see those kind of glass booths up there on that second level. That's where the translators were in there. Amazing thing, these translators, that you can hear one language coming in one ear and then you're saying the same words in a different language. It's really an amazing thing to listen to. They work shifts, they rotate. It's pretty stressful for them. But anyway, the governments are there. Each government has a placard in front of them with their country name. They sit alphabetically. The United States, I think, had 6 delegates, a mixture of scientists and State Department people. Some of you know Tom Carl, who's a climate scientist. He was one of the scientists that was on the US delegation. Up on the podium are the 2 co-chairs of Working Group 1, Thomas Stocker and Xin Dahe, Thomas from Switzerland and Dahe from China. There's members of the TSU. On the left side of that table is Melinda Tignor at a laptop. She's in charge of bringing up these sentences in an MS Word document of the Summary for Policymakers. They're projected on those 2 screens to the left and the right of the podium so everybody in the room can see it. And then she is typing in things as people are making changes in track changes. And so it's pretty stressful for her to do this as well. If your chapter has a statement that comes up as they're going through the Summary for Policymakers, you have to go up and sit kind of on the right side of that table and be ready to either defend what you've written or debate or discuss changes that governments may want to make. And so this is about half the room, and the other half is kind of behind where this picture was taken. So this goes on for 4 full days and 2 nights. We went until 2:20 a.m. Thursday morning and 5:20 a.m. Friday morning to approve this 27-page document. So you say, okay, what could possibly take that long? This is just one example. So the first morning, Monday morning, after all the speeches, we start in, And okay, we bring the first sentence of the Summary for Policymakers up. And that's the first sentence there, that paragraph there. It's just an introductory sentence, right? So immediately the government started intervening. They didn't like certain things about it. One government in particular wanted to separate this past and future thing, because their point was the past is observations, the future is models. The past are things, are facts we know of, the future is models, and we don't really know if the models are correct or not. Other countries are arguing, no, that's not right. You can't do that because you got to have it all together. This discussion went on for 40 minutes. At the end, we decided to just take out past and future, which is outlined in that box there in the top paragraph. And the final approved version was basically the top version, but without those words in it. You know, you're thinking, what possible difference can this make? And this is what you're saying through most of this 4 days. What possible difference can this make? But these governments are very deliberate and they're very detail-oriented. And for scientists, it's really frustrating. And if you're a diplomat, I guess this is what you do all the time. Okay, so for some results, this is a group photo was taken at the first lead author meeting in Kunming in southern China. There was improved treatment of regional climate information. And this climate phenomena chapter, which is chapter 14, had specific sections on changes in monsoons, El Nino, and things like that, as well as regional climate. There was this atlas of future projections that other working groups and other researchers can use, just tons of plots of all kinds of different quantities that came out of the models that you can look up and use if you want to. There was a lot more on clouds and aerosols. Aerosols are visible air pollution, including geoengineering, what possible things we could do to mitigate climate through geoengineering. Sea level change got a lot more attention because there's been a lot of work done on sea level change since the AR4. The carbon cycle is now much more studied. There's a lot better tools in terms of studying the carbon cycle, especially looking for changes due to ocean acidification. That's kind of a new thing. And we broke down the future climate change into two chapters. One was the near term and one was the long term. And just to say a little bit about the near term, is the governments actually brought this up, and this is one of these cases where the governments were reflecting what was happening in the scientific community. So in terms of a science problem, when you're trying to decide what's going to happen over the next decade, you have to take into account this kind of interplay between internally generated, naturally occurring climate variability and the response from things like increasing greenhouse gases. So this is a very challenging science problem, because usually what you do is you look at changes at the end of the 21st century after you've had all these big increases in greenhouse gases, and that's the main thing that's changed, and you get these big signals. But to look at decadal predictions is really a challenging problem, and it's of interest to stakeholders and governments. So for planning purposes, for example, water resource management, you don't want to know what's happening in 2100, you want to know what's going to happen in 2025. So this new field of climate science, which has just started up really since the AR4's decadal climate prediction, it's looking at this kind of middle area there between kind of initialized weather predictions, where you take the initial state of the atmosphere and run the model out for a couple weeks and try to track individual storms as they're going along, as opposed to looking at the end of the 21st century where you have this big increase in greenhouse gases and you're just getting kind of the response of the system to that change, that big change in atmospheric composition. In the middle, you get these decadal predictions where you use this initialization methodology where you start the whole model out, atmosphere, ocean, land, and sea ice, with the observed state at some time. Then you integrate it forward in time and you try to see how the statistics of regional climate evolve with time. So that was kind of a new area that was recognized scientifically and also from the stakeholder perspective as something that should be assessed. The models keep improving. There was roughly 45 of these standard models that were in this so-called coupled model intercomparison project phase 5 database, or CMIP5. This is where all the groups run the same experiments and put them into a big archive that everybody can analyze. 14 are so-called high-top models that have stratospheric dynamics. You have basically model levels going way up in the stratosphere to resolve stratospheric processes that could affect things lower down in the atmosphere. There was only one of those in the previous generation of models in CMIP3 that was assessed in the AR4. 19 are Earth system models, which are defined with at least interactive ocean biogeochemistries. In other words, you can put in the actual emissions of CO2 into the air, and the system handles that. So the ocean absorbs CO2 and maybe emits it. Plants soak up CO2 and emit oxygen. So you get all these processes that are going on where You can track things like ocean acidification much better and effects on the biosphere of climate change. There were 19 of those. There was none in CMIP3 of the standard generation of models. Prognostic, in other words, predictive air pollution schemes that can resolve not only the visible effects of the air pollution, but the effects of the air pollution on cloud brightness. Air pollution actually makes clouds brighter, which means they reflect more sunlight to space, so that's an additional cooling effect that a lot of models didn't have in the previous generation of models. It's pretty important, obviously. Correcting errors using the so-called flux correction technique to deal with model errors. There was none that were using flux correction in the current generation of models, and about a third were using that in the previous, in the version that was assessed in the AR4, so that's an advance. In terms of scenarios, there's a whole story behind these, how we came up with these future climate scenarios called representative concentration pathways, or RCPs. Basically, there was 4 of them. 3 of them were mitigation. So for the first time, we were assessing scenarios that actually required some intervention of governments in terms of policy. In other words, to steer the direction of energy usage or steer economic development or population types of issues. And so the idea is that there are things that you can do with policy that can actually make the climate change not as bad. And these 3 lower ones have mitigation steps incorporated in them, and the high one really doesn't have any mitigation. The interesting thing about this low scenario, RCP 2.6, which is highlighted as the green one there, and the center panel is the emissions, as you can see that green line goes below 0 right around 2070. So for this to achieve the climate change in RCP 2.6, which is designed to give you no more than 2 degrees centigrade warming above pre-industrial values, which is a target that's been listed by a lot of governments as something that's desirable. To achieve that target, you have to have negative emissions by about 2070. So what that means in this scenario is you have to be taking more CO2 out of the air than you're putting in by the year 2070. Big challenge, obviously. But one of the rules that the people that produce these scenarios have is you can't count on miracles. You have to use technology that you have now, that you know works. You have to apply it, though, in certain ways to give these outcomes. And so there are so-called carbon capture and storage methodologies out there. We know that technology exists to take CO2 out of power plant emissions, for example. It's done, actually, now for industrial purposes. But, of course, that would have to be applied on a massive scale, and you'd have to figure out where to put all that CO2. But, in theory, it could be done. So that's how you can get negative emissions by 2070. A lot of people after the AR4 were critical in saying, well, you guys are ignoring the sun. Everybody knows that it's the sun that's producing climate change, and you guys are ignoring it. Well, of course, that's not true. There was material assessed in the AR4 about solar influence on climate, but there was a lot more work that's been done, some here at NCAR actually, since the AR4, and we could actually make this statement for the first time in an IPCC assessment that got to the summary for policymakers, basically saying it's not the sun. We've measured changes in solar output, and it hasn't been increasing. You can't explain the global average temperature increase by increases in solar output. There are some mechanisms that we've identified that can produce regional patterns of climate variability from solar variability, but it's not having a global effect, at least since the mid-20th century, and cosmic rays aren't doing it. That's another popular thing that bloggers love to say. It's all cosmic rays, and you guys ignore cosmic rays. There's been a number of papers now looking that cosmic rays aren't having an effect. Okay, so there were some things that were familiar from previous assessments. This is kind of a standard plot that's been in all the assessments. It's the observed temperature anomalies starting out from sometime late in the 19th century and going up to near present. And you can see that overall there's a warming trend, so that's nothing new. We also put in this plot showing decadal averages, showing that the most recent decade is the warmest one on record. But there was this awareness of this kind of leveling off of the temperature increases since about the year 2000, the so-called early 2000s hiatus. So in the bullet that ended up being approved, that one there at the bottom, the US and a couple other governments in particular wanted that last sentence in there as a cautionary kind of caveat that's saying if you calculate trends based on very short records, depending on the starting and end points, your trend can be fairly misleading compared to a much longer trend calculated over a much longer record. So that was an example of a clarification point that was in the technical summary and the chapters that they wanted brought up to the summary for policymakers, which we did. But then the idea was that it's not just temperature, there's multiple indicators of climate change that have been observed. So these are all observations from various sources. Spring snow cover, you can see, has been decreasing there at the top. At the bottom there, Arctic summer sea ice extent has been decreasing. There's measurements now that have been put together looking at global average upper ocean heat content, which has been increasing. That's that top plot, again indicating a warming climate. Sea level's been increasing, again an indication that at minimum, because as the ocean warms, warm water expands, and as the warm water expands, as it gets warmer, sea level goes up. And so that's one kind of indication of increasing heat content in the ocean is sea level is going up. Biogeochemical cycles, there's more and better measurements now. There's the familiar plot there on the top of increasing CO2, which just keeps going up, of course. But the interesting plot here is the lower one. The blue lines there are increases of CO2 actually measured in the ocean surface layers. So CO2 is being forced into the ocean. The ocean is actually absorbing some of the CO2. And a consequence of that is that lower line, those green lines, is the ocean pH is going down, which means that the ocean is becoming more acidic. And so this ocean acidification, again, is another indication of climate change that is part of the system. This is a very complicated plot that's, for anybody that's followed the IPCC, a version of this plot has appeared in every one of them. These are all the things that affect the climate system, warming or cooling. So the bars that are to the right there are a warming effect, the bars to the left are a cooling effect, and you try to figure out what is causing, which of these so-called forcing factors are contributing. The top bar there, the big red one, CO2 is the big one, obviously. That's one of the biggest drivers, but there's a lot of other things going on. The new part of this is kind of just below the middle there, where it says aerosols and precursors. For the first time, we have information on individual types of air pollution that cause either cooling, to the left there, or the gray bar to the right, warming from black carbon aerosols, which is basically soot in the air from burning things. So we have a better estimate of that. And right below that is that gray bar with the big air bar that's going to the left there, which is cooling, which is the effect of air pollution on clouds. Air pollution makes clouds brighter, which means it increases their reflectivity, which means it reflects more sunlight to space, so that's a cooling effect. So these are all the combinations of warming and cooling factors that affect the climate system. So one of the things that people follow in these assessments is the so-called smoking gun statements. These statements connect human activity to climate change in a direct way. And so this is kind of a history of the smoking gun statements through the assessments. The first smoking gun statement was in 1995, and this was the famous balance of evidence statement. The balance of evidence suggests a discernible human influence on global climate. The words highlighted in red are the words that were argued about and debated in great detail. It's a kind of a qualitative statement, but it does connect human activity with climate. And this was why certain denier communities jumped on this, because they thought, okay, now these guys are getting serious. They're really now connecting what we're doing in terms of burning fossil fuels to climate change. And now we got to get serious about defending ourselves. So that was one of this statement, that single statement, was one of the reasons why that report got attacked, and they've been attacked ever since. Going to the third assessment report, the statement was, there is new and stronger evidence that most of the warming observed over the last 50 years is attributed to human activities. The word most there was debated and argued about. So this was in Shanghai in 2001. The first words that were in there were that a significant amount of the warming observed was attributed to human activity. Several governments said, we can't agree with significant amount. They formed a little contact group. Those governments went off to some scientists to discuss alternate wordings. They came back with most. We're sitting there thinking, okay, most, significant amount. Which is the stronger word? You know, so you get into these shades of meaning in these English words. But most stood in there, so that was what came out. Then, in the fourth assessment report, now we get to the point where we're certain enough we can actually put a likelihood statement in there. So most, that word's still in there, most of the observed increase, nobody still knows exactly what most means, but that's still in there. Nobody argued about that. They argued about very likely. Very likely in this case means you're 90% sure that this is a true statement. And there were several governments that wanted that degraded to just likely. They wanted to take the word very out of there. That means you're 66% sure. So they wanted to weaken it. And this argument went on and on for a long time. The scientists dug in their heels. They said, no, very likely is justified. And that's what came out. And that was the statement that came out there. So there's actually two statements that are now smoking gun statements in the fifth assessment report. One is this headline statement is extremely likely. Okay, now it's up from very likely to extremely likely, which is 95% sure, that human influence has been the dominant cause of observed warming. And then, in kind of in the detailed bullets, there's this extremely likely that more than half. So now we've actually defined what most is. Most is more than half, apparently, to some people. There's a lot of argument about what that meant. So those two statements, even though the previous ones had all been argued about at great length, both those statements breezed through. There was not a single government comment about these. And we were just stunned because we thought for sure they were going to argue that extremely likely was too strong. No, they had other things in mind. The reason we can make these kinds of statements is you look at this kind of a plot, and the blue, and you look by region, these are from climate models, the blue lines there are indicating what happens in the climate models if you don't have increasing greenhouse gases in them. The red lines are when you do put greenhouse gases in the models. And the black lines are the observations, and you can see the only way you get the observations is if you have greenhouse gases in your models. And of course, there's many other more detailed statistical methodologies to attribute this, but that's kind of one of the bottom line things. Because there's a lot more on sea level rise this time, and I kind of wanted to go through this relatively quickly. A couple of rates. The rate from prior to 1990 was about 1.5 millimeters per year. Since the 90s, early 90s, it's doubled to 3.2 millimeters per year. So that's some new information. The causes of the sea level rise, the volume of the ocean, of course, has to increase. As I mentioned before, thermal expansion from the warming of the ocean, warmer water is expanding, so that's one of the contributors. But you can add mass to the ocean by melting glaciers that are on land. So when a glacier on land melts, that water goes into the ocean, adds volume to the ocean. Ice sheets on land can melt, go into the ocean. And you can reduce water storage on land. So if you're pumping water out of aquifers, for example, and that runs off into the ocean, that adds water to the ocean, and that increases sea level. So for the first time, and the sea level rise people were very excited about this, they think they were able to close the sea level rise budget for the 20th century. So these are the various contributors. Thermal expansion is the biggest one at the top there. Glaciers have contributed a certain amount. The Greenland and Antarctic ice sheets have contributed a little bit so far. Land water storage has contributed a little bit. When you total all those up, you get that total contribution line there near the bottom. And there's overlap with the observed observations of sea level rise. And that overlap is something that they'd never been able to achieve before. And so this was considered really a new, or at least an exciting result for them, that we can really account for all the different sources of sea level rise that we've observed so far. And we have different levels of confidence, various likelihood statements, to these various kinds of things. So when you look at future projections of sea level rise, you can see that the highest end of the high scenario there, that red shading that goes all the way up to almost a meter of sea level rise, was higher than what was in the AR4. This is because the sea level rise community can now take into account possible future contributions from melting from Antarctic and Greenland ice sheets. That's the main kind of new thing they've been able to do. That gives them a higher number than what we had in the AR4 because we couldn't really account for that very well in the AR4. So in the AR4, we actually got criticized for being too conservative. We didn't have estimates that went up as high as a meter. Our estimates went up as high as about 0.8 of a meter, but this time we have at least a high estimate that goes up to a meter by 2100. And we get different rates. The earlier the CO2 gets emitted, the more sea level rise you get. Of course, then there's these kind of doomsday scenarios. What if the West Antarctic ice sheet collapses? And again, a lot of this is being studied. A lot of this is really unknown, but this has to be assessed because there's papers out there now looking at this. If this happened, obviously the sea level rise projections would be a lot higher than what they said the likely range was that I just showed. But they think, and they have medium confidence, which is kind of not real strong, that the additional contribution wouldn't exceed several tenths of a meter. So it's not like a couple more meters if the Antarctic ice sheet, West Antarctic ice sheet melted. It's just a few, several tenths of a meter. So that's maybe not as alarming as what some people had estimated before, but we don't really know. And so that was kind of those statements that they put in there to address that kind of issue. Sea level rise is also going to have a pattern to it. It's not just going to rise the same amount everywhere. This is a plot showing when the darker red colors are greater sea level rise in certain regions, where the lighter colors are less sea level rise in certain regions. This is because the ocean's absorbing different amounts of heat in different regions, and the winds are changing such that the winds are pushing the water around in different ways in the future climate that contributes to these regional changes of sea level rise. Just a little bit more about these projections now. The top plot here is kind of a traditional plot showing the 20th century climate model simulations in the gray, and then you go into the future and you have the high and the low scenario with the intermediate ones there and to the right. Two new pieces of information on this plot. The middle one shows changes in Arctic September sea ice, and you can see the red shading in that red line that kind of drops down there by 2050. That dashed line is what the sea ice community defines as a nearly ice-free Arctic. And apparently there's areas in the Canadian islands and other places where you always have little pockets of sea ice. It's almost impossible to melt them. But to get basically the whole center of the Arctic to be ice-free, the estimate was based on a subset of models that did the best job of simulating 20th century sea ice changes. Those are the red shading and the red line there. So the conclusion then was that we could have an ice-free Arctic in September by mid-century. So that was kind of a headline statement, because a lot of countries are very interested for a lot of reasons in what's going to happen to sea ice in the Arctic. Another new plot here is at the bottom showing projections of ocean acidification. You can see that for the high warming scenario, the red line, it's going down, which means pH is going down, which means acidification is going up. And if you have basically the unmitigated climate change, you get a lot more ocean acidification than if you have the mitigation case for the low scenario. This again is another kind of plot. A version of this has been in previous assessments, showing on the left-hand side from the low scenario, the right-hand side is the high scenario, showing you get a lot more climate change when you have a lot more CO2 in the air. The new part of this plot, the top panels are there, the temperature, second row is the precipitation, third is the sea ice, Arctic sea ice, and you can see on the left there you get a lot of sea ice in the low scenario, hardly any sea ice in the high scenario by 2100. But the new plots here at the bottom, this ocean acidification, so showing that you get a lot more, the ocean has a lot more acid in the high scenario with a lot more CO2 in the ocean. Okay, there's this thing that's been going on called the early 2000s hiatus, and if you look at the black line in this plot, you can see that it's kind of leveled out since about 2000. So this has, of course, drawn a lot of interest. Here at NCAR, we've done a lot of work on this. The other lines in this plot are the model simulations. You can see that most of the model simulations for that time period in the 2000s lie above the actual observations. So this has caused a lot of criticism from various quarters saying all the models are wrong. No models have simulated this early 2000s hiatus, which is actually not quite true, because you can see some of these models actually do lie over the early 2000s hiatus, just because their internally generated variability happens to sync up with what was happening in the real system. And we've done work on this. I'm actually going to give a seminar on this in a few weeks. But the statement that was very carefully crafted assessing the literature so far, and this literature was moving so fast that it was really difficult. This was a case where papers were coming out almost every couple weeks on the hiatus. And so there's a line that they draw. They say, okay, after this time, we can't assess any more papers because we have to send it out for review. But basically, the assessment was it's a combination of internal variability, kind of debris from a collection of small volcanoes that kind of reflected sunlight over this time period, and maybe solar variability, solar output was a little bit less. I think from the work that's been done since then, it's probably mostly internal variability in the climate system that's been temporarily able to offset the warming from the increasing greenhouse gases that these particular models that didn't take those observations into account didn't get. But for my chapter, we were trying to assess what the climate was going to be like in the near term. And the standard kind of near-term time frame was 2016 to 2035. So the top plot here is just the observations in black with all these model simulations from the so-called uninitialized free-running traditional models, not getting much of the hiatus. But when you look at the middle panel, and those kind of hatched areas are from this new technique of decadal climate prediction that I was talking about earlier, where you start out the model with observations, say in the year 2000, and you see what the next decade produces, and those models produce less warming. And they actually show some agreement with the observations for the observed hiatus. and they actually produce somewhat less warming in the future compared to these kind of more standard models. So this is something that we've been trying to communicate, and it's difficult to communicate because we're saying these are the same models that are being used with these uninitialized. And when I say uninitialized, you start the model out in 1850, for example, and you run it through the 20th century, right into the 21st century with these scenarios, average them all together, and get some response to basically increasing greenhouse gases. And you're trying to average out this internal variability that's producing these interesting decadal changes. But with this initialized decadal climate predictions, you're actually trying to resolve that internal variability as well as the response to the increasing greenhouse gases, and you do get somewhat less warming. And that bottom panel shows that black bar there is the range, and you can see that it's less than the range from the gray shading from the uninitialized model. So that was kind of a result that surprisingly didn't get much attention. What did get most of the attention is this last little piece I'm going to be talking about here. If you say we're increasing CO2, like in that top plot, and you just stopped it, and CO2 emissions could somehow magically go to zero, in models you can see in that second panel there, the concentration actually doesn't go to zero. The CO2 stays in the air because it has a long lifetime of hundreds of years, and the temperature doesn't go back to zero. The temperature pretty much stays at some level. So you can imagine a series of experiments where you can take the emissions to zero at different times, and you can see that you get different levels of warming that just kind of keep hanging around. So what this means is you have a method by which you can directly connect the accumulation of CO2 emissions over time with the temperature change. And so this is a very simple schematic showing that if you plotted cumulative emissions across the bottom and temperature increase on the y-axis, you could go to say, okay, my cumulative emissions up to this time are this, go up to that line, go across to the temperature increase line and say, that's caused that much temperature increase. So the implication of a plot like this for governments, and this is why they were extremely sensitive to this, is now you have a formula for computing damages. So if you calculate an inventory for your country and you've emitted a certain amount of CO2 accumulated from some time period, say from 1850 to present, and you know what that number is, you go to this plot like this and go across and you say, okay, your emissions have accounted for this much of the warming. So, okay, maybe the U.S. has emitted a certain amount, and you can figure out, okay, the U.S. has contributed to 60% of the warming so far. That means the U.S. has to pay damages that have occurred for that warming, in 60% of those damages, to developing countries who haven't emitted anything. So this is and we didn't know this going in, scientists, and they start arguing about this plot. So this is the plot that was actually produced in chapter 12, Claudia's chapter. And this is the plot where they actually were able to calculate cumulative emissions against temperature change. And you can see it's roughly linear. The line's basically going up at a 45-degree angle, which means you can go across and figure out these damages. So this just got a lot of discussion. And basically the developed countries wanted more uncertainty put into this. You just can't go up to this line and go across and get one number. You got to have thresholds, and what are the probabilities of certain things happening. So all of this, of course, is implied in this figure. And in the 6 hours from 11 p.m. to about 5 a.m. on the last night, they were trying to decide how to actually present this information. They added this bullet giving various thresholds and probabilities of 33, 50, and 66%, and basically saying that there's uncertainty involved with these different numbers. But this turned out to be the most sensitive and the most kind of provoking figure of the whole Summary for Policymakers that, as scientists, at least I didn't anticipate this would be that big a deal because it's scientifically trivial. It's a really nice, clean result. Got a linear relationship. You never get linear relationships in the climate system. But these governments just really were sensitive to that. Okay, just the last slide here. The printed version, even though it was all approved in September 2013 in Stockholm, the printed version got printed about 3 or 4 weeks ago. It's available on the IPCC webpage or through Cambridge University Press. Working Group 1, like I said earlier, there's 3 working groups. We're done. Working Group 2 is winding up here in a couple weeks. There are plenaries in Yokohama. Working Group 3 is ending up in April in Berlin. There's a synthesis report that kind of tries to synthesize all information across all 3 working groups. That's going to be finished in October. And then we're done. And then, of course, is there going to be an AR6? Like I said earlier, the governments, not the scientists, make this decision. There were sessions at AGU and AMS where the scientists were complaining that we should have more say in this, whether there should be an AR6, because it's a huge time commitment for the scientific community. But it's basically the governments that make this decision. The governments ask us to do it. If the U.S. government asks us to participate in this, we get funded. A lot of our funding comes from the U.S. government. We're obligated really to help them out and give them this information. It's something we should do anyway. So if they want this information, we'll comply, but it's unclear what kind of information they're going to want. They'll probably meet sometime in 2015 to make this decision. So we'll see what happens. That's all I had. Thanks.